Whether you realize it or not, yields are in your everyday life. Whether you actually yield your full paycheck to take home is a matter of how much your country is taxing you. And that is a sad thing. You will never yield your full paycheck, inevitably. So today, in chemistry context, we'll be talking about theoretical, actual percent yields. By the end of this video, you should be able to calculate for theoretical yields and determine the percent yield using a value of actual yield. So if you think about it, even in terms of baking cookies, if you like chocolate chip cookies as much as I do, or as much as my husband does, albeit he doesn't like the actual cookies themselves as much as he likes the cookie dough, I'm fairly certain at some point he is going to have some kind of stomach bug by the amount of cookie dough that he consumes. Raw eggs. Ugh. So what does it mean when we look at this recipe that says yields 3 dozen cookies? What does that mean exactly? Hopefully you know that a dozen means 12 and 3 times 12 is 36, and that word yield means it's going to give you 36 cookies if you were to follow said recipe verbatim. Now, if I followed this recipe exactly as it's stated, and there's no dough left over, and I rolled each ball exactly the right diameter or circumference or whatever, according to the recipe, I would theoretically be able to yield a maximum of 36 cookies. Now, granted, if I made the balls smaller or if I made the balls larger, then I would have less cookies or more cookies respectively. So that would also change the yield depending on what I do with the size of the cookies. Or as in my example here, when I bake chocolate chip cookies, I mentioned that my husband, Mr. Duckonta, will always eat at least 2 raw cookie dough balls. And I'm not talking small balls here. Like, he will literally take a whole handful of cookie dough out of my mixing bowl. Against my will, of course. So when he does that, my actual yield of my cookies, even though the recipe is supposed to yield 36 cookies, is now less than 36 cookies. So if he took out 2 of those raw cookie dough balls from my mixing bowl, I would now yield a maximum of, say, 34 cookies, albeit I'm pretty sure it's less than that by the huge handfuls he takes out. So chemical reactions are exactly like baking cookies. In fact, baking cookies is a chemical reaction. That's why you have to add all the different ingredients together, including baking soda and baking powder, so that the cookies rise. That is chemistry in itself. So just like the chocolate chip cookie recipe, the ingredients that we mix together are our reactants, and the cookies are the products at the other side of our equation arrow, if you will. Therefore, any recipe or any chemical reaction will yield a certain number of cookies or a certain number of product, a certain amount. So what we can say then is that we'll have this value that's a theoretical amount of product that we should be able to make if we were to follow the recipe verbatim, and if everything in the world aligned perfectly, all the stars in the sky and all the flowers were facing the sun perfectly on a bright summer day, for whatever reason everything is exactly perfect, then that's the maximum theoretical amount we could make using that recipe or chemical reaction. But as I mentioned, everything would have to align. The stars would have to align, all the flowers would have to be blossoming at the same time. Everything would have to be exactly perfect Goldilocks kosher zone, and we all know that that's not possible. It's not possible to have everything in the world exactly perfect. So our actual yield is always going to be different than our theoretical yield. Typically less, but it can be more. So our actual yield is going to have some kind of contaminant, maybe making it more than what we anticipated, or maybe it doesn't all react the way we thought it should, and so we'll actually end up with less product. Either way, our actual yield is really never going to be the theoretical yield. They'll never be equal. So then what is this theoretical yield? That's the calculated amount of product that could be produced from a reaction, i.e. our dimensional analysis, our magical line to freedom. So just like I said, I could have 36 cookies according to the recipe. That would be my theoretical yield. Theoretically, as well, you can make a certain dollar per hour for your paycheck, the wage at your job or your future job. If you wanted to be, I don't know, in the military, a basketball player, if you wanted to be a nurse or maybe a car mechanic, whatever it is you want to be, that job or that career typically has a certain dollar per hour wage associated with it. And that is what you can theoretically bank on bringing home in your bank account. But as I mentioned before, do you actually ever take your whole paycheck home? No, of course not. And that's where taxes come into play, or your actual yield, what you actually get to take home. That's the amount of product actually obtained in a lab from an experiment, if we're thinking about it in terms of chemistry. Or the fact that I actually end up with 34 cookies instead of 36 because my husband will inevitably eat cookie dough out of the mixing bowl. Or, again, after taxes, the actual amount that you take home from your paycheck is different than what you should theoretically be making. So go ahead and pause the video here and really take to heart what I was saying earlier. The planet isn't perfect. Neither is anyone in it. I know you'd like to believe you are, but you're not. Neither am I. Nobody is. Can a chemical reaction, therefore, ever yield 100% of the expected products, of the theoretical products? Go ahead and pause here and think about it and why. Hopefully you remembered that I was talking about the fact that you can have more than your theoretical, or you could have less than your theoretical in an actual yield. Because in a chemical experiment, you could always end up with contaminants, adding more mass to your product. Or you could have the fact that your reactants don't all react the way you want them to. Maybe the temperature was off, maybe it needed to be hotter or cooler, or maybe there was some kind of condition in the lab that wasn't met for all the reactants to react to produce the correct amount of theoretical products. So the actual is never going to be 100% of the theoretical. This is where percent yield comes into play. Since no reaction will ever yield 100% or more unless there's errors again, or unless there's contaminants, then you could have more than 100%, of course. And that's where a future topic, percent error, will come into play. But for now, while we're talking about percent yields, scientists need a way to communicate how much percent of the products was actually made. So how much did we actually get versus how much we wanted to get or we should have gotten in a perfect world. And to do so, we're going to use the following mathematical setup. Actual yield divided by theoretical yield times 100 will give us percent yield. So let's give this example try it a go before we jump into the chemistry. If you were going to work at Taco Bell for $10 an hour before taxes and you work 20 hours per week, what would be your theoretical weekly income, i.e. your theoretical yield? If you know that you're working for $10 an hour and you're working for 20 hours, you would multiply those two together and that would give you $200. So theoretically, if you worked 20 hours per week, you'd be making $200 per week. Or if you were looking at this in terms of a month, there's 4 weeks in a month, so you would be making $800 per month. However, once income taxes come about, and we're still not even talking about like healthcare and everything else that also gets taken out of your paycheck, just thinking about income taxes here. If income taxes take out 10% or $20 from your $20 per week from your earnings, what is your actual yield? What do you actually get to take home and spend on your Starbucks coffee later this week? Your actual weekly yield would be the 200 minus 20 in this case per week. So you'd actually be taking home $180 per week. Or if you want to think about it monthly, you'd only be taking home $720 per month instead of the $800 that you would theoretically be taking home if it wasn't for taxes. So now we can use this information and figure out the percent yield. What is the actual percent that you are bringing home from your actual over theoretical? So our actual is 180 per week divided by our theoretical, which is 200. And we're going to take that and multiply it by 100 according to our equation that I gave you earlier. When you do this math, you find out that you're actually only taking home 90% of what you're making. And now, of course, that value is much higher than it should be because we're not taking into account healthcare and all that other stuff and Medicare, Medicaid, and everything else that comes out of our paychecks. So it would be great if we were actually taking home 90%. It's actually much less than that. So here are the steps you need to know before we jump into the chemistry. Step 1 for calculating percent yield is that we need to first calculate for the theoretical yield using our dimensional analysis, our stoichiometry.
Oh, no.
In other words, you need to determine the limiting reactant using our option 1 strategy. If you don't know what I'm talking about, please go back to my limiting reactant video linked in the description below. There are 2 ways to solve for limiting reactants. We're going to go with option 1, which calculates for grams of products from both reactants that we are given, and then use that value to determine how many grams can be made based off of the limiting reactant. Step 2 is to find the actual yield. Whether the actual yield, if in some normal problem on a test or on a worksheet, will be given to you most of the time. That's the mass that you weigh at the end of your experiment. So if you were trying to calculate percent yield for a lab situation, you would need to go back to your data and see how much your product weighed at the end of the experiment. That's your actual yield. And then step 3 would just be to plug those 2 values from step 1 and step 2 into the actual divided by theoretical times 100 to give you that percent yield final answer. Let's try it together with chemistry this time. Given the following chemical equation, before I even read the question, I'm going to double check and see, oh yeah, there are coefficients in front of this chemical equation, so I can kind of assume that it is balanced, but let's double check real quick. We have 4, 8, 12 oxygens here, plus 4, 8 oxygens. So on the reactant side, we have 20 oxygens. On the product side, we have 4, 8, 12, plus 4, 8, also 20 oxygens on the product side. That's balanced. We have 2 P's on the product side, and we have 2 P's on the reactant side. We have 2 irons here and 2 irons here. We also have 3 sulfurs on the product side, and we have 3 sulfurs on the reactant side. Everything balances in this chemical equation, so we can move forward with the math part. If I performed that above reaction with 25 grams of iron 3 phosphate, well, which one of the reactants is iron 3 phosphate? It's got to be this one. That one has the iron atom in it. And there's 25 grams of that. So let's write that on our balanced equation. We have 25 grams of iron 3 phosphate, and we have an excess of sodium sulfate. So the question is already telling you that this one is in excess. Therefore, we know that the iron 3 phosphate must be the limiting reactant. How nice that they, in a roundabout way, told us which one's the limiting reactant so we didn't have to do an extra calculation. Now the question is saying, how many grams of iron 3 sulfate can I theoretically make? So how many grams of the iron 3 sulfate could be made using our limiting reactant as our given for dimensional analysis? As always, we're going to draw our magical line to freedom in order to figure out how many grams of the iron 3 sulfate could be made, starting with 25 grams of iron 3 phosphate. This is a grams of one chemical to grams of another chemical setup. We know we're going to have the pattern that we've always had for these, where we have molar mass, mole ratio, molar mass, and then finally, our final answer. Let's jump over to our periodic table and find the molar mass of iron 3 phosphate. Each iron weighs 55.8. Each phosphorus weighs 30.9. And each oxygen weighs 16. We happen to have 4 of those, so 16 times 4. When I add all of those values together, that'll give me the molar mass, which happens to be 150.7 grams of FePO4 for every mole of iron 3 phosphate. Now I need to use the mole ratio to get rid of the iron 3 phosphate and convert it into the chemical of iron 3 sulfate, our goal chemical. So we need to look back at our balanced equation and notice that there's 2 moles of iron 3 phosphate for every 1 mole, there's an invisible 1 there, of iron 3 sulfate. Our goal mole will always go on top. The 1 mole of iron 3 sulfate will go on the top, and the 2 moles of iron phosphate will go on the bottom. Now for our last step, we need the molar mass of iron 3 sulfate. Looking back at our periodic table, we can see that each iron again weighs 55.8, and there's 2 of them. Each sulfur weighs 32, and that's rounded down here, and there's 3 of those. Don't forget the little 3 on the outside of the parentheses multiplies in. So there's 3 sulfurs. Each oxygen weighs 16, and now that 3 is multiplying into 4. So 4, 8, 12, we actually have 12 oxygens. So my final molar mass for iron 3 sulfate ends up being 399.6 grams per 1 mole of iron 3 sulfate. Let's go through and make sure all of our units cancel before we plug it all into our calculator. Here we see that the grams cancel here, Mole cancels here with the correct chemical canceling. And moles of iron 3 sulfate cancel here. We are left with our goal units, so we know we can plug and chug into our calculator now. We've got 25 times 1 times 1 times 399.6, all divided by 150.7 times 2 times 1. So that gives us 9,990 divided by 301.4, for our final answer is 33.14 grams of iron 3 sulfate could be made from our limiting reactant, the 25 grams of iron 3 phosphate. In other words, theoretically, the maximum amount of iron 3 sulfate that we could make in a perfect world, if all of the stars aligned just right, we could make 33.14 grams of iron 3 sulfate, maximum. We're going to take that number and now figure out the percent yield. If we did a lab and we found in the lab that we only obtained 18.5 grams of iron 3 sulfate, so that's how much we actually got at the end of our experiment, what was the percent yield? Well, we already did the calculation for theoretically. So theoretically, we should be able to make 33.14 grams maximum. Let's plug and chug into our skeleton equation for percent yield. We're going to take the actual amount that we got in the lab, the 18.5 grams. We're going to divide it by the theoretical amount, 33.14 grams. Multiply that by 100 for our percent yield. So those of you out there that are Breaking Bad fans, when it talks about Mr. White being like 99% yield for the methamphetamine that he was synthesizing, that's like near impossible, like legit near impossible for even chemists that are the best chemists in the world. Just an FYI for you. When I do this division, I end up with 0.558. When I multiply by 100, that's just like moving my decimal over 2 spaces. So I technically have a percent yield of 55.8%. So I only got a little over half of what I should have gotten for the product that could have been made in a perfect world scenario. Now that you've seen me do one, go ahead and try one yourself. According to that chemical equation between aluminum and copper 2 chloride, if I had 0.3 grams of aluminum reacting with excess copper 2 chloride, that's a big hint right there, and 0.44 grams of copper actually isolated in a lab, so this 0.44 grams is your actual yield, figure out the percent yield. Go ahead and pause the video here and give it a try. All right, now that you've had a chance to try it on your own, let's give it a try together and make sure you did it right. First off, don't let the fact that they give you the actual yield up front scare you. Just because I gave it in 2 different steps for you to see it and not be as frightened by it, now that they give it to you, don't forget this is the actual. We still need to calculate the theoretical first. You still have to do dimensional analysis first so that you can get to the percent yield calculation setup. So let's go ahead and draw our magical line to freedom with a space for our answer. And in this case, we're going after the copper. They gave us the actual amount of copper isolated, so that is the product that we are interested in. So let's calculate for grams of copper that could theoretically, in a perfect world, be made using 0.3 grams of aluminum. This is a grams of one chemical to grams of another chemical setup, meaning it's the molar mass, mole ratio, molar mass setup. We need the molar mass of aluminum, so look to your periodic table to find the molar mass of aluminum, which happens to be 26.9. So let's go ahead and plug 26.9 grams of aluminum for every mole of aluminum. Again, remember, if you wanted a mole of aluminum, you'd weigh out 26.9 grams, and you've got a mole of it. Now we need to get rid of aluminum with a mole ratio. Our mole ratio comes from our balanced chemical equation. We've got 2 moles of aluminum, 2 moles of aluminum, for every 3 moles of copper, 3 moles of copper. Now, I didn't go through the checking of the balanced equation here, but if you did, good for you. Pat yourself on the back. You should always check before you calculate to make sure that the equation is correctly balanced. Next, we need the molar mass of our copper, our product of interest. Looking back at our periodic table, we see that it weighs 63.5 grams of copper in every mole of copper. Make sure your units cancel before you calculate. We have grams of aluminum canceling, moles of aluminum canceling, moles of copper cancel, and we are left with our goal units, so we can plug it into our calculator. We're going to take our 0.3 times 1 times 3 times 63.5, all divided by 26.9 times 2 times 1. That setup gives us 57.15 divided by 53.8 for a total of 1.06 grams of copper that could theoretically be made. Now we only have one more step. We know what was actually made and we know what should have been made. So let's take our actual 0.44 grams divided by our theoretical 1.06 grams and multiply that by 100. And our final percent yield is 41.5%, so less than half of what we should have gotten in this chemical reaction. If you'd like a challenge, go ahead and pause the video here and see if you can figure out what your actual yield would be given the following information. You have uranium reacting with bromine to form uranium hexabromide. If you started with 100 grams of uranium and you got a percent yield of 83%, what was your actual yield in the lab? Go ahead and pause the video here, see if you can figure it out. Whenever I'm given these kind of questions, I like to figure out what is the piece that's missing. You can solve any math equation if you have all the pieces except for one. So in this case, the thing that I'm missing is my actual yield. That would be like my X value in math, for example. If that scares you because throwing letters and numbers together is scary, you can always just draw a smiley face. Heavens, you could just say, we're going to solve for the smiley face over the theoretical yield times 100 gives me my percent yield. Now, what is it that they give you so we can take away some of these unknown values in our setup? They give us a percent yield of 83%. So let's go ahead and plug that in after our equal sign. How about the theoretical yield? That's like another X or Y. We can't have two variables to solve for, so we need to get rid of theoretical. The way we're going to do that, of course, is by using 100 grams of uranium to solve for the amount of product we could make. Dimensional analysis to the rescue! Oh no! Here comes our magical line to freedom. We have 100 grams of uranium, and we're trying to figure out how many grams of product we could make from that. As we always do, check your periodic table for the molar mass of uranium to get rid of grams of uranium. The molar mass of uranium is 238, so 238 grams per 1 mole of uranium. That'll get rid of our grams of uranium. We need the mole ratio now, which happens to be 1 mole of uranium to 1 mole of uranium hexabromide. That's pretty convenient. And now we need the molar mass of uranium hexabromide. We have 6 bromines, and each bromine weighs roughly 80 times 6. And we already saw that uranium was 238. So add those two values together, and we get 718 grams of uranium hexabromide per mole. Our moles of uranium cancel here, moles of uranium hexabromide here. We are left with our goal units, so now we can plug and chug. We have 100 times 1 times 1 times 718, all divided by 238 times 1 times 1. When we do that math, we get 301.68 grams of uranium hexabromide as our theoretical yield. So now we can get rid of this unknown in the denominator of our setup. So now we should have smiley face, that's what we're solving for, divided by 301.68 times 100 equals 83%. Now we just have to do some reverse math. In order to undo the multiply, we're going to divide both sides by 100, and that'll give us smiley face divided by 301.68 is equal to 0.83, because now we're just moving the decimal point backwards on our percent of 83%. Now to undo and solve for our smiley face alone, we need to get rid of the 301.68 on that side and move it to the other. The way we do that mathematically is to multiply both sides by 301.68, so that top cancels here and bottom cancels there. What I do to one side, I have to do to the other, 301.68. So multiplying those two together. And that'll give us a value of 250.39. And that's what our smiley face, or our X, is equal to. 250.39 grams would be my actual yield. That's what I actually got in the lab. So if you were doing a lab experiment and you forgot, and maybe you misplaced, how much you actually obtained in the lab through your calculations, you can always do this as a workaround going backwards to figure out how much you got in the lab. Before you wreck yourself with this Alka-Seltzer equation. If you were going to mix Alka-Seltzer, sodium bicarbonate, with hydrochloric acid, your stomach acid, you produce table salt, water, and carbon dioxide. Hence, that's the reason why you can use Alka-Seltzer to stop a tummy ache. If you were going to use 5 grams of sodium bicarbonate, your Alka-Seltzer, and it produced 1.5 grams of table salt, NaCl, what was your percent yield? If you want to know if you got this answer correct, please watch my next video where I will go over this calculation in specific. Please give this video a quacks up, and I hope your day is just ducky. See you later.
No ducks, no glory.